Now the next result, so now some remarks or note you can make it. Suppose intersection of an infinite number of open sets in a metric space is always open. In R1, for example, infinite number of open sets, that is a countable collection of open sets if a union that is open. Just now we proved it. But same thing is not possible with intersection. If there is an infinite collection of open sets, if we intersect them, then we cannot assure that the resulting set is also open. For that one, we are going to give some example. In R1, in real line with usual metric, In denotes an open interval. Just we are defining it. In is an open interval in Rn. It is of this type. An open interval minus 1 by n comma plus 1 by n. Then if you intersect all these intervals In, so for example, so what happens is, so what is that n I1? So I1 is minus 1 to plus 1, all these points inside this is I1. So what is I2? Minus 1 by 2 plus 1 by 2, all points in this. So what happens if n is increasing? What happens? You see this the size of the length of the intervals keeps on reducing it, and eventually if you intersect everything, will contain only one element, that is 0. This intersect contains only the element 0, and already we proved that, and 0 is not an open set in R. Already we proved that singleton sets are not open in real line with usual metric. Therefore, what we come to the conclusion here is, if we intersect infinite number of open intervals, it's not true that, not always that the resulting set is also open. Resulting set is also open. Okay. So this is an example. For this example, we collected all intervals like this type. If we intersect it, it contains only 0. 0 is not an open set. So this remark you can keep and make a note of it. However, finite collection of open sets, if you take it and do the intersection, then that is open. That is what we are going to prove it. That is, we are going to prove it. Theorem. You can prove by induction, but now first at present we will take two open sets, G1 and G2, and we will show that G1 intersection G2 is also open. Now, then by induction we can show that G1, G2, G3 so until Gn are n open sets, then intersection of them is also open. We can prove by induction. If G1 and G2 are open subsets of the metric space M, then G1 intersection G2 is also open. I'm going to prove it. G1 intersection G2 is also open. Let us assume that this intersection is non-empty. Because if it's empty, already we proved that empty sets are open. So now let us assume that G1 intersection G2 is non-empty. Let us take one general element of G1 intersection G2. So this implies that X is element of G1 and X is element of G2. Now X is element of G1 and X is element of G2. I can write like this: X is element of G1, comma X is element of G2, and G1 and G2 are open sets in the given metric space M. Open sets of M. So what I can come to the conclusion is, there exist open balls. There exist open balls, say B of X colon R, contained inside G1. Say instead of R1, I will put this as R1. And another open ball B, the same center with radius R2. This is contained inside G2. So this is possible because of G1 and G2 are open sets. Now let us say, now create a new variable, that is R, which is nothing but the minimum of R1 and then R is minimum, then this open ball whose center is X and radius is this R is contained inside G1 intersection G2. That is, for this R minimum, this will be inside G1 as well as G2 for that radius, because any two elements whose distance is less than R1 will be inside G1. If the distance between an element and the X is less than R2, it will be inside G2. If it is distances between any element and the X is less than R, which is less than R1, R2, then it will be in both of these two sets. So what we proved is, we took one element in G1 intersection G2, then we proved that the entire open ball is inside this intersection. So which implies G1 intersection G2 is an open set of M. So to prove that, suppose G1 intersection G2 so until intersection Gn is also open, you can prove easily by induction, method of mathematical induction. That is, we have proved for n equal to, we assume that it is true for n equal to k, then you can prove the result for n equal to k plus 1. Okay, so this is by induction you can prove it.